I'm Rupesh Kumar. I build the quantum communication systems. I got an idea, then I build it. So I recently come to York, started a lab in computer science department where I build systems. So I simplify the slides. Sometimes it's very oversimplified, but you will enjoy it, I think. So quantum communication with the classical system. So I'll be talking about communication and then some security of these communication systems. Smoke, fire, the oldest way of transmitting message for long distance communication is also fire. We still use fire for when we, no pop, black smoke and yes pop. Radio, so you have radio signals, you modulate the amplitude. AM radio, you have FM radio, frequency modulation. Now we have fiber optics things. We have the laser, so laser transceiver system that you have the laser light here. You modulate it, then you can translate the light. I was thinking when I see this laser pointer, I can transmit my heartbeat by pressing here normally. I'm nervous, so someone can read my heartbeat from that vibrations. So these classical communications, they are, different things, on, off, no smoke, different modulation, they are distinguishable. You can distinguish. I'm talking a classical way because you can distinguish it. Anyone can interfere this message and then read the message. So what is security? Yeah, to make it secure, we use cryptography to encrypt the data with a key and decrypt the data. Encrypt the data with the key, and then you send it, and then you decrypt the message using the same key or different keys. Skytel is used by Spartans. The cylinder, you have the leather tape on it. The message is written in this way. So you need the same cylinder to read the message. So the cylinder is the key here. This is an example. But the security of the systems are based on mathematical assumptions. If a brilliant mathematicians can break many of these crypto systems, or a powerful computer like a quantum computer can break some of these encryption systems. So two types of encryption systems. One is using different keys for encrypt and decrypt. One is use the same key. The quantum computer can possibly break these different key systems that we are actually using right now in our Gmail password encryption systems. So we use quantum communication for transmitting the keys. Transmitting key is a problem. How do you securely transmit key between the same key between two different persons? So we use quantum system photons. But photons, they are wave, sometimes particles, so we use that coherent state or Fock state in quantum optics. Let's talk about how do we make it indistinguishable. So the message must be indistinguishable for a third party. So how do we make it? So we make it with the quantum superposition. It's called superposition. I'll tell you what. Quantum uncertainty. You don't know exactly what is the quantum state that you sent. So no one can make a copy of it except the legitimate user. It's called no cloning. So how do you make quantum superposition? You take a photon and split it. So you get different dimensionality of this quantum state. So this is a simplest way, but let's see. So let's imagine you have 100 photons you're sending to a beam splitter. You get 50 photon there and 15 photon there, right? But when I send one photon, no, you cannot split a photon. Yeah, what you do actually, you have the probability of photon here and there, but in a quantum mechanical way, this is a superposition. So what you make here something called a qubit, a two-level quantum system. The photon can be in one level or two level. It's like a bit 0 and 1. A photon can be in this bit 0 and 1 at the same time. Example, polarization of the light, the way it vibrates, the electromagnetic field, the electric field vibrates, the polarization. You can have the horizontal polarization and the vertical polarization, but you can make a superposition by combining them together. So this is called a polarization qubit, a quantum bit. So how do you send this key using a quantum bit? Here, I have a horizontal or vertical basis where I can encode the key in a different polarization. Also, I can make the vertical, diagonal and anti-diagonal polarization and encode the keys. To retrieve the key, Bob the receiver uses a single photon detector because we are talking about single photon for few photon systems. Bob has to measure the polarization of the light in a proper measurement system here. For the other bases, Bob has to rotate the signal and use the same system. So you have to use a proper measurement system for each of the bases. If you don't use it in a proper measurement systems, you start to make errors. And you can detect these errors. So when you transmit a key using a photon from one user to other user, and someone is trying to measure it, and the eavesdropper or Eve try to measure it, and Eve doesn't know which basis Eve has to measure, she generates the error. You detect that error, and if the error is above some threshold value, don't use the key. If the error is below, use the key for cryptography. But in New York, here, we are using the coherent state, coherent property of the light. The coherent state or coherent communication is actually right now happening in the fiber communication. You cannot send a lot of data just by switching on and off the laser, but you can send the data by different levels of laser intensity, different phase. So it's like here. So different amplitudes and different phase of the light. So here you can pack more than a bit in one single transmission. So we use the same idea, the amplitude and phase of the light, but it has millions of photons. That is not quantum. To make it quantum, you attenuate that into near to the vacuum. Then you started to see the quantumness there, which means you cannot really precisely estimate the amplitude and the phase of the light because of the Heisenberg uncertainty principle. So Ali sent this key, encode this on different quantum state and send to Bob. Due to attenuation, still this light comes near to the vacuum. An eavesdropper in between tries to detect it. She doesn't know the exact state, so she has to recreate with a bigger uncertainty. And Bob detects the bigger uncertainty. So it's like an excess noise in the detection system. If the noise is below some threshold value, use the key. If that above, trash it, start again. So this is an idea, but we have invented a system that can transmit the quantum and classical signal at the same time. So we start with that. You have the quantum keys on the quantum signals, which is near to the vacuum, which means that there is less photons there. But what you have done, we displace the light from near to the vacuum to different directions. So the directional displacement tells which classical bit value you are encoding. So we have invented this system, and then we have patented by the university. So this system can generate this kind of displaced quantum state with the classical and quantum data on it. I'll use this experimental setup to demonstrate this work, and then we got this result. So you can see different classical data format there. So this is what received by Bob, the scrambled message. We extract the classical data. You see this is distinguishable clearly. After this extracting the classical data, then we go for the extracting the quantum key. So this technique, it is able to send quantum and classical data on a single pulse. So another work that I'm right now concentrating on free space quantum communications. Right now, so everybody is going to have this communication from satellites or free space or high altitude platforms flying 20 kilometers above the atmosphere, above the ground level. So here the problem is you send a beam of light, and this beam of light has a divergence, so you cannot collect all the light, so this is a loss. So what I have, so one day I got a call from our business manager. Okay, we are trying for this one, but these telescopes are really costly. What to do? I started with a stupid thought, but I ended up like here. So it's like a single transmitter, but you have many small telescopes together, which are very cheap. Then you can have high transmittivity. You can collect many more light, and this works like the array of radio telescopes. You have a giant telescopic effect, but you have small telescope. So the good thing is it increased the channel transmittivity. It is low cost compared to bigger telescope, and it generates new protocols, like you can encode the data on different spatial modes of the light. So the receiver, if I make a copy of this receiver and put that there, it's a transmitter, meaning multiple transmitter and multiple receiver. which is right now is a hard subject, something called a MIMO, which we use for mobile communication. So you have many transmitters, many antennas, many receivers. Then you can fight the noise with this technique. So a PhD student is going to start to work on that system, quantum MIMO. So this is the work, and I'm working with these people in different departments, physics and Tim Spiller, and Stefano in computer science, and David Grace in electronic engineer. And I want to thank the Quantum Hub supporting people, Georgie and Cletus, for giving me, because they are behind me, behind my growth in Quantum Hub. Thank you. I assume you will be in any of these states. Yeah.